Imagine you're standing on top of a tall building. You drop a car and a ball at the same time. The question is, which one will hit the ground first? Most people think the car will fall first because it is heavier. But if there is no air resistance, both the car and the ball reach the ground at the same time. Now, the next question. When we release an object, why does it fall downward? Why doesn't it move upward, away from the Earth? Now, one more question. Are the car and the ball really falling downward, or is the ground actually rising up to meet them? At first glance, this sounds strange because we assume that objects fall while the ground remains still. According to Newton, gravity pulls objects toward itself. That's why they fall downward. But Einstein explained it differently. According to Einstein, objects do not actually fall. The Earth bends the space-time around it, and objects move along this curved path and end up colliding with the Earth. In other words, the car and the ball continue in straight motion, but the curved space-time of the Earth brings them toward it. Now the question is, since Earth is round, if the same experiment is done on the opposite side of the planet, meaning if an object is dropped there as well, will Earth also rush upward on that side and collide with the object? If that were true, Earth would have to run in every direction, colliding with everything. And in that condition, our planet would have shattered long ago. But that doesn't happen. Why? Because Einstein never meant that Earth literally jumps like a ball to hit falling objects. Einstein said that massive objects bend the space and time around them, and other objects simply move straight through this curved space. In other words, Earth is not running anywhere. T simply curves the surrounding space-time in such a way that from every direction, things appear to move toward it. Now the question arises, so who is right, Newton or Einstein? The real answer is both. Newton's theory works perfectly for everyday life. But when it comes to extremely high speeds, massive objects, or extreme phenomena like black holes, Einstein's theory becomes more accurate. Now the next question, why does the moon orbit the Earth? Why doesn't it escape into space? Or why doesn't it crash directly into Earth? Actually, the moon is moving very fast forward, while Earth is pulling it inward with gravity. Because of the balance between these two forces, the moon keeps revolving around Earth. In the same way, Earth is also falling toward the sun. But at the same time, Earth is also moving rapidly forward. Because of this balance, Earth remains in orbit around the sun. Now comes the question of black holes. A black hole's event horizon is the boundary beyond which even light cannot return. At this point, space-time becomes so extremely curved that every path leads inward toward the black hole. So anything that crosses this boundary becomes trapped forever inside. All the questions we've asked so far point to one single thing, gravity. But the real question is, what exactly is gravity? Most people think gravity is a pulling force. But the truth is much deeper than that. Gravity is actually the curvature of space-time. If gravity did not exist, there would be no stars, no planets, no galaxies, and no life. The entire universe would be filled only with gas and dust particles. Gravity is an invisible structure that keeps the whole universe in balance. Imagine if gravity disappeared for just 5 seconds. Everything would start floating in the air. Water would rise upward. Cars and buildings would become unstable. Earth's tectonic plates would begin to shift. And when gravity returned, whatever had gone up would crash back down with full force. That's when we realize how dependent our everyday life is on gravity. Thousands of years ago, people only knew that things fall downward. Why they fall, there was no scientific explanation. Then came Aristotle, who said that heavy objects fall faster than light ones. And for nearly 2,000 years, the world believed exactly that. About 425 years ago, Galileo Galilei proved through real experiments that all objects fall at the same speed. This is where the true scientific journey of gravity began. He dropped a light ball and a heavy ball together from the Tower of Pisa. Galileo observed that both balls hit the ground at the same time. From this, Galileo proved that the speed at which objects fall has nothing to do with their weight. whether the object is heavy or light. If both are released at the same time, they will reach the ground together. Galileo's concept overturned Aristotle's 2,000-year-old belief. This became the first solid scientific step in human history toward understanding gravity. However, Galileo still did not have the answer to one important question: why do objects fall downward? Then, about 410 years ago, a scientist named Johannes Kepler studied the behavior of planets. Kepler carefully observed how planets move and created his own laws explaining how a planet's speed around the sun is related to its distance from the sun. Kepler gave 3 laws about the solar system. The first rule stated that planets do not revolve around the sun in perfect circles, but in ellipses. An ellipse has 2 centers, and the sun lies at one of its foci. This means a planet sometimes comes very close to the sun and sometimes goes very far away. This was the first time someone proved this scientifically. Kepler's second law said that when a planet passes close to the sun, it moves faster, and when the planet is far from the sun, it moves slower. And Kepler's third law stated that the farther a planet is from the sun, the longer it takes to complete one orbit around it. For example, Earth completes 1 revolution around the sun in 1 year. Jupiter takes 12 years to complete 1 orbit, while Neptune takes 165 years to go around the sun once. Friends, Kepler created his own laws about the planetary system, but even Kepler himself did not have an answer to why all this happens. He only explained how it happens, but why it happens, even he did not know. Now let's go back about 360 years. At that time, England was going through a crisis because a deadly plague was spreading rapidly. Due to this, all schools, colleges, and universities were shut down, including Cambridge University. At Cambridge, there studied a 23-year-old thin and quiet young man who mostly stayed lost in his own thoughts. His name was Isaac Newton. While people were fleeing cities to escape the plague, Newton also returned to his village. One day, Newton was sitting under an apple tree outside his house. A gentle breeze was blowing, and sunlight was breaking through the clouds. Suddenly, an apple fell to the ground near him with a soft sound. He kept looking at the apple, and a question flashed through his mind. Why does an apple always fall downward? Why doesn't it rise up into the clouds? It was a small question, but that question shook the entire world of science. Newton began to think, if an apple falls from above to below, does the earth pull the apple toward itself? And if the earth can pull an apple, could this pulling force also act on other objects? Then Newton wondered, if apples fall downward, why doesn't the moon fall? After all, the moon keeps moving around the earth. But what is the difference between falling in space and moving in orbit? A third question came into Newton's mind. Is the same force that pulls an apple down also keeping the moon in Earth's orbit? Friends, this question in Newton's mind became a turning point in human history, because now both the direction and destiny of science were about to change. Newton thought that just like the apple falls toward Earth, the moon is also falling toward Earth. But the moon is not only falling downward, it is also moving sideways. Because of this sideways motion, the moon keeps circling the Earth. This means the apple and the moon must be experiencing the same force. But this force cannot be uniform. As the distance from Earth increases, this force must decrease. That means objects closer to Earth experience a stronger force, and objects farther away experience a weaker force. In other words, as we move away from Earth, Earth's ability to pull objects toward itself becomes weaker. And as we come closer to Earth, this pulling power becomes stronger. Then Newton said that every object attracts every other object. And we call this force gravitation or gravity. Friends, Newton discovered gravity when he was just 23 to 24 years old, but he did not publish at that time. Finally, after 15 years, in 1687, he published his great book Principia Mathematica, in which Newton's laws of gravity were presented to the world. Newton expressed gravity in the form of a mathematical equation. Newton's gravity formula is F equals GMM2 slash, our superscript 2, I hope you must have studied this formula at least once in school. Now, friends, a question may come to your mind. Okay, according to Sir Isaac Newton, the same gravitational force is acting on both the apple and the moon. Earth's gravity pulls the apple toward itself, and Earth's gravity also pulls the moon toward itself. Now the question is, why doesn't the moon fall onto the Earth? Why does it keep going around the Earth instead? To understand this, we take a simple experiment called the cannonball experiment. Imagine this is the Earth, and on Earth there's a very tall mountain. On top of this mountain, there's a cannon that fires iron balls. If the cannonball is fired at a low speed, the ball will move forward, but Earth's gravity will pull it back, and it will fall to the ground. Now, if we fire the same ball with a slightly higher speed, the ball will travel a longer distance, but in the end, gravity will again pull it down. Increase the speed even more. The ball will go even farther, but it will still eventually fall back toward Earth. So far, everything seems normal. Now here's the important point. The Earth is round. Because of this, as the ball moves forward, the ground also slowly curves downward. Now, imagine we give the ball so much speed that Earth's gravity keeps pulling it downward every moment, but the ball's sideways motion is so fast that each time it moves forward before it can hit the ground. What will happen in this situation? The ball will keep falling continuously, but it will never hit the ground. Instead, it will start moving around the Earth. This is called an orbit. Actually, orbit does not mean that an object is not falling. Orbit means falling continuously, but missing the ground every time. The moon works on this same principle. Earth's gravity keeps pulling the moon toward itself, and the moon's forward motion keeps it from crashing into Earth. Because of this balance, the moon keeps revolving around Earth. This is called a free-fall orbit. The moon is falling toward Earth every moment, but because of its sideways motion, it misses Earth every time, which means gravity keeps pulling the ball downward, but because of Earth's curvature, the object keeps missing the ground. Friends, this is exactly how the moon revolves in Earth's orbit, and all satellites and space stations sent into space are also in free fall. In the same way, Earth and the other planets of our solar system orbit the sun. Now, friends, think for a moment. What if we fire the cannonball with even more speed? In that case, the ball will move forward so fast that although Earth's gravity will try to pull it back, the ball will have so much speed that it will overcome Earth's gravity and go straight into space. Meaning, because of its high speed, the ball will not stay in Earth's orbit at all. Friends, this is called escape velocity. Escape velocity is the minimum speed needed for an object to overcome a planet's gravity and leave it. Friends, Earth's escape velocity is 11.2 kilometers per second. So it's approximately 400 kilometers per hour. That means if you throw a ball upward at a speed of 11.2 kilometers per second, it will leave Earth forever and go into space. Now, friends, every planet and star has its own escape velocity. The stronger the gravity of a planet or star, the higher its escape velocity. Friends, about 350 years ago, Sir Isaac Newton gave an explanation of gravity that was so perfect that you could calculate the orbit of any planet, the path of any asteroid or comet, and even the tides rising in the oceans. Using Newton's laws of gravity, almost everything could be predicted. At that time, the whole world thought that the secret of gravity had been discovered. Science was considered complete. Newton became a legend in his lifetime. For nearly 200 years, no one dared to question his theory. But about 145 years ago, in the German city of Ulm, a child was born into a simple family. That child was different from other children. He started speaking late. He had a calm nature. He was considered an average student in school. Some teachers even called him slow-minded. But there was something special inside that child, a deep curiosity to understand everything. That same child later became Albert Einstein. As he grew up, Einstein started working as a clerk at the Swiss Patent Office. But his real strength was his imagination. He would spend hours lost in thought, diving deep into the mysteries of the universe. Once he imagined, If I sit on a beam of light and travel at the speed of light, what would the world look like to me? This single question went on to change the direction of physics. Now listen carefully. According to Newton, gravity is a force, and that force acts instantly. Let's understand this with an example. Imagine you tie a heavy ball to one end of a rope and hold the other end, spinning it in circles. The rope keeps pulling the ball toward you, and the ball keeps moving around you. Now think, what if the rope suddenly breaks? The moment the rope snaps, the ball immediately stops moving in a circle and shoots outward in a straight line. This change happens instantly. According to Newton, gravity works exactly like this, as an instant force. But Einstein couldn't accept this idea. Einstein knew that light from the sun takes about 8 minutes and 20 seconds to reach Earth. Now, Earth revolves around the sun, meaning the sun's gravity keeps Earth in its orbit. Einstein asked a question: what would happen if the sun suddenly disappeared? According to Newton's instant gravity, the moment the sun vanished, its gravity would vanish too. And just like a ball flies away when a rope suddenly breaks, Earth would immediately leave its orbit and shoot off into space. But here comes a big problem. The information that the sun has disappeared would take at least 8 minutes to reach Earth, because light itself takes that long. And there is a fundamental rule of the universe: nothing can travel faster than light. So how can gravity be instant? This is where cracks appear in Newton's theory, and Einstein's new way of thinking is born. In the universe, no information can travel faster than the speed of light. Even light itself has a speed limit in this universe, which is about 300,000 kilometers per second. Now, friends, just think about this. If the sun suddenly disappeared, how would the information that the sun is gone and its gravity has ended reach the Earth before light does? Because the fastest thing in the universe is light itself. The last light emitted by the sun would still not have reached Earth yet. But before that, Earth would already leave its orbit and drift into space. This thought experiment shook Einstein's mind because it created a contradiction. The information about gravity disappearing was reaching Earth before light, which breaks the fundamental law of the universe. As I just told you, the law of the universe says that nothing can travel faster than light. From this thought experiment, Einstein realized that something was wrong with Newton's gravity. There was something missing in Newton's theory of gravity, something that was creating this contradiction, because the universe cannot break its own rules. But what exactly was that missing piece? This question took away Albert Einstein's sleep at night. In a small Swiss patent office, a simple clerk was sitting, but inside his mind, an entire universe was running. Suddenly, Einstein heard the sound of a bell because someone was coming up in an elevator. At that moment, Einstein completely froze and started thinking, if the elevator that man is riding suddenly snaps its cable and begins to fall freely downward, what would that man feel inside the elevator? Friends, this question may sound small, but Einstein's thinking turned it into a universe-changing thought experiment. Friends, try to imagine Einstein's thought experiment yourself. Suppose you're on the top floor of a tall building, coming down in an elevator. Suddenly, the elevator cable breaks, and the elevator starts falling toward Earth in free fall. In that situation, you would feel like you're literally floating. You wouldn't feel your body weight at all, because in free fall your body would not press against the elevator floor. You would see papers, books, and even yourself floating around. Meaning, when the elevator is in free fall, you wouldn't feel any force inside it. Literally, you would feel zero gravity. That means, in a free fall condition, the effect of gravity disappears. Now, friends, imagine that everything you see in the universe disappears. Earth, the moon, the sun, even all the galaxies. Meaning, everything in the universe that creates gravity vanishes, and you are left completely alone in this silent universe. Now, since there is no gravity in space, in this situation you would feel completely weightless, just like how you feel inside an elevator that is in free fall. Listen carefully to what I'm saying and try to connect the dots. In free fall, an elevator is falling from a tall building, and you inside the elevator don't feel the floor at all because you're unable to apply any force on the elevator floor. Now imagine another scenario. There is no gravity in the universe, and you are freely floating in space. Now assume that in this free-floating condition, you're inside an elevator. So friends, in both of these scenarios, you feel the same thing, zero gravity. But why? In the free fall situation, where did Earth's gravity suddenly disappear for you? The moment the elevator hits Earth's surface, you start feeling your weight again. You notice that your feet are pushing against the elevator floor. As soon as the elevator touches the ground, you feel gravity. It feels as if gravity has returned for you. Now, let's move to the second scenario. Suppose the elevator floating in space suddenly starts accelerating upward. In this case, as soon as the elevator accelerates upward, the floor pushes against your feet, applying force and pushing you upward. You literally feel as if you're pressing your feet against the elevator floor. Inside the elevator, you start feeling your weight again. It feels as if gravity has appeared. This force is exactly like when you're sitting in a bus and the bus accelerates forward. You feel a push backward. Friends, let me tell you, many people get confused between speed and acceleration. If you understand acceleration, then consider that you have understood gravity. Imagine a car moving at a speed of 100 kilometers per hour. This is its speed or velocity. But the car speed was not always 100. At the beginning, the car was at rest, meaning its speed was 0 kilometers per hour. As soon as you press the accelerator, the car starts moving forward. But the car does not instantly reach 100 kilometers per hour. It speeds up gradually. First 10, then 20, then 30, and in this way, step by step, it reaches 100 kilometers per hour. This increase in speed is called acceleration. That means, as long as the car's speed keeps increasing, the car is accelerating. When the car finally reaches 100 kilometers per hour and maintains that speed, acceleration ends, and the car starts moving at a constant speed. Now, an important point. The greater the acceleration of the car, the stronger the backward push you feel. And if the acceleration is less, this push also feels weaker. This push happens because your body wants to remain in its previous state, that is, at rest. If an elevator is free floating in space and suddenly starts accelerating upward, the floor of the elevator will push against your feet. Or you can say it this way, your feet apply force on the floor, and the floor pushes you back with equal force. That's why you feel as if you've suddenly become heavier. In reality, this isn't any mysterious force. It's simply the effect of acceleration. And this is exactly where Einstein shows us that there's a deep connection between gravity and acceleration. Now, friends, if an elevator accelerates upward at 9.8 meters per second squared, then your feet will apply exactly the same force on the elevator floor as they do when you're standing on Earth. Do you understand what this means? That gravity is nothing else. It is acceleration itself. This thought experiment shook Albert Einstein's mind, and only one sentence came out of his mouth. Acceleration and gravity are not different. They're the same thing. Acceleration and gravity are the same thing. Now Albert Einstein understood this much, that gravity is not a force at all. Rather, gravity is an illusion, a misconception. It behaves like a force, but actually it isn't. And Albert Einstein's thought experiment challenged Newton's centuries-old law of gravity. Newton described gravity as a force. But according to Einstein, gravity is not a force at all. Now, friends, if gravity is not a force, then the question still remains, what exactly is gravity? So, to understand gravity, let's once again go back to that elevator which is freely floating in empty space, where there is no gravity. Assume that the elevator has no acceleration. In this situation, you would also be freely floating inside the elevator. Now, if you throw a ball straight ahead, that ball will travel in a straight line and hit the front wall of the elevator. So friends, the path of the ball will appear to you as a straight line. But now, let's assume that the elevator starts accelerating upward. And once again, you throw the ball forward. In this case too, the ball will continue to travel along its same path, a straight line. But from your point of view, the ball's path will appear curved. This happens because the ball is still moving in a straight line, but the elevator itself is accelerating upward. So the elevator floor actually goes up and collides with the ball. But from your point of view, it feels like you threw the ball forward. Yet the ball follows a curved path and falls downward. Now think about this. When you throw a ball forward on Earth, because of Earth's gravity, the ball also moves forward while following a similar curved path. Now, friends, imagine this. Instead of a ball, you're holding a torchlight. What would happen then? Let's assume that the elevator has no acceleration at all. It is just freely floating in empty space. In this case, when you turn on the torchlight, the light beam will appear to travel in a straight line and hit the elevator wall. But if the elevator starts accelerating upward, then you will see that same light beam bending. It will look as if the light beam is following a curved path. Now, friends, here you might argue, okay, we accept that the path of a ball inside the elevator and the path of a ball on Earth are exactly the same. But then why is it that when we turn on a torchlight on Earth, the light beam does not appear to travel in a curved path? So, friends, the answer is actually very simple. Let's assume that an elevator is accelerating upward at 9.8 meters per second squared. Friends, this acceleration is exactly equal to Earth's gravity. In this case, light will bend, but it won't bend so much that we can actually feel or notice its curvature. You remember escape velocity, right? As we know, Earth's escape velocity is 11.2 kilometers per second. If any object is thrown at a speed of 11.2 kilometers per second, it can overcome Earth's gravity and escape into space. Now, as we also know, the speed of light is many times greater than Earth's escape velocity. Light travels in vacuum at approximately 300,000 kilometers per second. So you can think for yourself, can Earth's gravity really affect light? Friends, Earth's gravity does try to bend light, but that curvature is so small that we cannot feel or see it with our eyes. But friends, if we keep increasing the elevator's acceleration again and again, then as the acceleration increases, we will start seeing light following a curved path. Are you able to understand what I'm trying to say? Now, this much we already know. That acceleration itself is gravity, meaning the greater the acceleration, the more light will bend. And the greater the gravity, the more it will bend light. I hope everything makes sense to you up to this point. Now, friends, let me ask you something. If acceleration itself is gravity, then we know that an elevator accelerates upward. That's why, inside an elevator, we feel gravity. But the Earth is not accelerating upward. So why do we feel gravity on Earth? Friends, Albert Einstein gave a very interesting answer to this question. He said that we feel gravity on Earth because spacetime itself is being pulled toward the Earth. Now, what does that even mean? Friends, before understanding what gravity really is and how it works, you first need to understand space. Space is like a stage on which the universe performs its acts. Just as a magician is incomplete without a stage, in the same way, the universe is incomplete without space. A magician needs a stage to perform magic. And inside that stage, there are many hidden secrets that the audience cannot see. On that stage, the magician uses those secrets to perform magic tricks and entertain people. If you look closely, the magician's real magic is hidden in the backstage of the platform, which people cannot see from the front. Friends, the universe itself is a very big magician. And this universe magician needs a stage to show its magic. And that stage is space itself. Friends, whenever I say space, what comes to your mind? Do you imagine an empty place? Let's imagine space. Suppose everything you see around you starts disappearing one by one. The car standing in front of you disappears. Your house disappears. The trees and plants around you disappear. The airplanes flying in the sky disappear. Even the earth beneath your feet disappears. And our sun also disappears. Now what do you see around you? You will notice that the universe is filled with countless stars. Let's assume they disappear too. Even a very last star in the universe disappears. There are no galaxies, no celestial bodies left in the universe. In this deserted universe, only you remain, and the entire universe is filled with darkness. Now tell me, what do you see around you? Do you see empty space? No. Whatever you see around you now, that is space. And let me tell you, space itself is not empty. Albert Einstein said that space is a physical entity in itself. Just like you can touch water, in the same way, you can also touch space. But the difference is this: when you touch water, you can physically feel it. You know you are touching water. The reason for this is that our body has limitations. It is restricted to a 3D world. That means we experience our world in 3 dimensions: length, width, and height. Within these 3 dimensions, we can move freely, and we can control these 3 dimensions according to ourselves. Everything physical that you see around you exists in 3 dimensions, whether it's a ball, an airplane, mountains, or even us humans. All of them are built in a 3D world. Even water molecules themselves are 3D structures. Even the smallest particle of the universe, an electron, also has a 3D structure. So friends, everything we see in this 3D world can be physically felt through touch. But space is different. Space itself is a 4th dimension in which our 3D world operates. Because space is a higher dimension, and our physical senses are limited only to 3 dimensions. We can touch space, but we cannot feel its physical form. If you've watched the movie Interstellar, there's a scene at the end where the main character, Cooper, falls into a black hole and reaches a tesseract. That tesseract is a 5-dimensional world where Cooper can physically see space-time. Just like we can touch objects in our 3D world, Cooper can literally touch space-time in that 5-dimensional world. Cooper is able to do this because he is in the 5th dimension, controlling the 4th dimension. If we talk about ourselves, we live in a 4-dimensional world, but from here we can only control 3 dimensions. In the same way, Cooper was controlling the 4th dimension, space-time, while being in a 5-dimensional world. On the other hand, Cooper's daughter was present, just like us, in a 3-dimensional world. Cooper could see her, but his daughter could not see Cooper. She only felt that some invisible force was around her, something that couldn't be seen, but was definitely having an effect. This is how higher dimensions work. A lower dimensional being cannot see a higher dimension, but a higher dimensional being can see lower dimensions. Similarly, space exists all around us, but we cannot touch it because it lies beyond our normal senses. But here's something important to understand. Space alone is not the 4th dimension. Actually, space and time together form the 4th dimension, called spacetime. Now the question arises, what exactly is spacetime? You'll get that answer later. But before that, it's important to understand space itself. Usually we think space means emptiness, but that's not true. Space exists, and it is not passive at all. It's just our limitation that we cannot feel it with our hands. Just like objects in our 3-dimensional world have physical properties, space also has its own properties. Take water as an example. Our water into any container, and it takes that shape. Throw a stone into water, and waves are created. You can bend water, make it flow, and even control it. In the same way, space is also a kind of fabric. It can be stretched. It can be compressed, it can be twisted, it can be bent, and even ripples can form in it, which today we call gravitational waves. Meaning, space is not an empty stage on which the universe is simply playing out. Space itself is a part of the universe, an active, dynamic structure. And when a place contains a large amount of mass or energy, space itself bends. This is where the real story of gravity begins. But in the universe, space is controlled by only 2 things, mass and energy. In Einstein's famous equation, E equals mc squared tells us that mass and energy are actually 2 sides of the same coin. This means one thing clearly. Wherever there is mass, there is energy. And wherever there is energy, space will definitely be affected. Now, try to understand space like this. Space is the stage on which the entire universe performs its show. Stars, planets, and galaxies are visible to us, but the space spread between them works like a backstage. Just like a magician needs a stage to perform magic, the universe also needs space to display its wonders. Now let's talk about space-time. If I ask you right now, where are you? You might say, in your room or in a city. But in reality, what you just answered is a specific point in space. If you say you are in Delhi, it means you exist at a particular location in space. In other words, everything in the universe has an address, and this address has two parts. First, space coordinates. That means where exactly something exists in the universe. But the story doesn't end here. Now imagine I ask, when are you in Delhi? Right now? 1 hour ago? Or tomorrow? This is where time comes in. So this means the complete address of anything is not just location. Time is also included. That's why Einstein didn't treat space and time as separate. He said that space and time together form a single thing, space-time. What we think of as space and what we think of as time is actually a four-dimensional fabric. And this space-time fabric is bent by mass and energy. When a massive object like Earth, the Sun, or a black hole exists, it creates a dent in this fabric. Nearby objects slide along the slope of this dent and move toward it. That is gravity. No invisible rope, no pulling hook, just the curvature of space-time. As we know, our world is three-dimensional. So in these three dimensions of space, at which point Delhi exists, that's the first thing you mentioned. The second thing you mentioned is time, meaning you are in Delhi at the present moment. Now, friends, if I ask you where you were 1 year ago, this time you would tell the address of the place where you were 1 year ago. If I asked where you were this morning or yesterday afternoon, it's possible that this morning you were at home and yesterday afternoon you were at your school, college, or office. What I mean to say is that your address always contains two things. First, the coordinates in three-dimensional space. Second, the time at which you were there. In other words, space and time are not two separate things. They are actually one single thing called space-time, and this space-time itself is the fourth dimension. Let's assume that you were at your home half an hour ago, and even after half an hour, you were still at your home. In this scenario, you did not travel in the three dimensions of space, but you definitely traveled in time, meaning you spent half an hour at your home in time. Now, if we assume that 1 hour ago you were in the market, and after 1 hour you are now at your home, then in this case, you travel both in space and in time. Time is something we can feel passing, but we cannot see it because space and time together form the fourth dimension. Friends, let me tell you something. Every single moment, we are traveling in both space and time. For example, if you say that you were at home half an hour ago and you are still at home now, that is actually incorrect because you are speaking relative to Earth. The real truth is that Earth itself is carrying you through space-time at thousands of kilometers per hour. And our Sun is carrying Earth through space-time. And our Milky Way galaxy is carrying our Sun through space-time. Now, friends, as I just told you, space is very flexible, and space-time can be controlled by mass and energy. So how do mass and energy control space-time? Let's understand this with an example. Imagine there is a rubber sheet in front of you. You can think of it as space-time. Now, if you place any object on this rubber sheet, it sinks inward and creates a curve. The heavier the object, the more the sheet bends. The exact same thing happens in the real universe. Massive bodies present in space-time, like stars and planets, bend the space-time around them. Now, if you place a big ball on that rubber sheet and roll smaller balls around it, the smaller balls automatically start moving around the big ball by following that curve. In reality, the small balls are not moving because of any pulling force. They're simply traveling along the path of the curved sheet. In the same way, planets don't orbit the sun because of some mysterious force. They They simply follow the curvature of space-time created by the sun. And the moon doesn't revolve around Earth due to gravity alone, but because of the bending of space-time created by Earth. This makes one thing clear: gravity is not an ordinary force. Gravity is actually the curvature of space-time. Massive objects bend space-time, and everything else moves forward by following that curved path. Friends, if we look at it, the rubber sheet experiment explains space-time and gravity quite well. But it is an incomplete truth, because in this experiment we see space-time only in 2D, whereas the reality is that space-time is spread all around us in 3D. Right now, the animation you're watching on your screen is a 3D visualization of space-time. And in reality, every star or planet bends space-time from every direction. If you notice carefully, space-time is bending from all sides and getting squeezed toward the center. Friends, this is actual gravity, the curvature in space-time. Because of this curvature in space-time, you, me, and everything in the world feel Earth's acceleration. And it seems to us that the Earth is pulling us toward its center. Whereas in reality, space-time itself is getting squeezed toward the center. This is gravity, or you could say that our Earth is accelerating through space-time and colliding with objects itself, rather than objects falling onto the Earth. But the Earth feels stable to us because this entire game of gravity is happening in a fourth dimension, which we simply cannot see. Our thinking is limited to 3 dimensions. That's why it feels like if Earth were accelerating in all directions, it should explode. But in reality, Earth is not accelerating in 3 dimensions. It is accelerating in the 4th dimension. And we are actually feeling that acceleration of the 4th dimension. Newton explained gravity according to our 3-dimensional world. For him, gravity was a force that pulls objects toward itself. But Einstein viewed gravity from the perspective of the 4th dimension, that is, space-time. This is why Newton's gravity feels simple to us, while Einstein's theory feels complex. According to Einstein, objects in space-time are actually at rest. They don't perform any special falling motion. In reality, it is the Earth that moves toward them due to the curvature of space-time. But this entire process happens in the 4th dimension. We only experience its result, which we call falling. We cannot see space-time bending, so it appears to us that objects are falling downward. That's why Einstein didn't call gravity a force, but instead described it as the curvature of space-time. Now the question arises, how did Einstein know that mass bends space-time when we can't even see space-time? The answer lies in his famous thought experiment. Einstein imagined an elevator freely floating in space. When this elevator is accelerated, the light traveling inside it no longer moves in a straight line. It appears to follow a curved path. The greater the acceleration of the elevator, the more the light bends. From this, Einstein realized that acceleration and gravity produce the same effect. And if acceleration can bend light, then massive objects can do the same. Meaning, the heavier the object, the greater the curvature of space-time. In the universe, light always travels in a straight line. But when it passes near a planet or a star, space-time is already curved. Light simply follows that curved space, and to us, it appears as if the light itself is bending. This is called gravitational lensing, and this became the strongest proof that mass truly curves space-time. Friends, Albert Einstein didn't talk about the curvature of space-time just in theory. He also proved it mathematically. According to Einstein, gravity is nothing but geometry. It is created by the curvature of space-time itself. Einstein's explanation also solved a famous paradox. If the sun suddenly disappeared, sunlight would take about 8 minutes to reach Earth. But people wondered, would the sun's gravity disappear instantly? Would Earth immediately fly out of its orbit? Einstein explained that gravity doesn't work like a signal traveling from the sun to Earth. Instead, the moment the sun disappears, the curvature of space-time itself vanishes. That's why Earth would leave its orbit. Not because information traveled faster than light, but because the geometry of space-time changed instantly. No law of the universe is broken here. Friends, in 1907, Einstein first had the idea that gravity might not be a force, but a geometric effect. And in 1915, he finally presented this theory of gravity to the world. Albert Einstein did give us the theory of space-time curvature, but this theory shook the entire scientific community. For the past 200 years, people had trusted Newton's gravity, which was easier to understand and felt more practical. But Einstein's space-time curvature theory was hard to understand even for the scientists of that era. Nobody could easily accept the idea that something invisible called space-time even exists and that it can bend. At that time, scientists had only one big question: was Einstein right or wrong? And how could this be proven? Because we cannot directly see space-time. Friends, there was only one way to test whether Einstein was right or not. According to Einstein, the more mass an object has, the more it curves the geometry of space-time. Now, in our solar system, there is only one body with the maximum mass: our sun. So, the sun should affect the geometry of space-time the most. The idea was simple. Imagine this is the sun, this is our Earth, and there's a star behind the sunlight. Coming from that star should normally travel in a straight line and reach Earth. But since the sun is in between, it should block our view, and we should not be able to see that star from Earth. However, if Albert Einstein was correct, then the sun's mass would have curved the surrounding space-time. Because of this curvature, the light coming from that distant star, while passing near the sun, should follow the bent space-time and curve toward Earth. And that means we should be able to see that star, even though it is actually behind the sun. But this method, which looked so simple, was actually not that easy, because the star whose position had to be measured appeared very close to the sun. And as we know, during daytime, the sun's light is so strong that the stars around it are not visible at all, which means the experiment was only possible if it became dark during the day. And during the daytime, there's only one thing that can block sunlight from reaching the Earth: our moon. When a total solar eclipse happens, the moon comes directly in front of the sun, and for a few minutes, daytime turns into something like night. At that moment, stars begin to appear in the sky. Now, scientists were waiting for just one thing: a total solar eclipse. Finally, a date was set: May 29th, 1919. The entire scientific world was waiting for this day. Then that day arrived. The solar eclipse began. Slowly, the moon started covering the sun. The sky began to darken, and stars became visible in broad daylight. This was the exact moment when Einstein's theory was going to be tested in the real world for the very first time. Scientists immediately took photographs of the stars using telescopes and recorded their positions. Later, these stars were compared with photographs taken on normal nights. And then the result came out. The positions of the stars had shifted slightly, exactly as Einstein's calculations had predicted. This made one thing clear: the sun had curved the space-time around it, and starlight had reached Earth by traveling along that bent path. This was not Newton's gravity. This was Einstein's general relativity, proven for the first time. And this single experiment made Einstein the most famous scientist in the world overnight. The star that was directly behind the sun now appeared above the sun. The star that was hidden behind the sun was literally seen above it, like an illusion, because the star was not visible at its actual position but appeared somewhere else. Albert Einstein was absolutely right when he said that gravity is not really a force. Gravity is the curvature of space-time. Friends, Albert Einstein also said that when two black holes collide, or two neutron stars merge, or when a massive star explodes in a supernova, ripples are created in the fabric of space-time, just like ripples form when you throw a stone into water. Einstein called these ripples in the fabric of space-time gravitational waves, and he said that these gravitational waves travel across the universe at the speed of light. Now, friends, here's something interesting. The concept of gravitational waves was proposed by Albert Einstein in 1916. But at that time, We didn't have any technology to prove whether Einstein was right or wrong. And it took a full 100 years to finally confirm his prediction. Friends, this happened on September 14th, 2015. In the USA, LIGO detector sensors measured very tiny ripples in space-time. In fact, two black holes collided about 1.3 billion light-years away from Earth, and the gravitational waves produced by that collision reached our planet. This was the first time the world directly observed gravitational waves, and Albert Einstein's prediction made 100 years earlier turn out to be absolutely correct. By now, we understand that the greater the mass of an object, the more it bends space-time. So the question arises, what happens in the case of black holes? Because black holes possess enormous mass, compressed into an extremely small region. That's why a black hole doesn't just bend space-time like ordinary objects. It almost completely destroys it. Let's understand this using Einstein's elevator thought experiment. Imagine an elevator floating freely in space. Now, as the acceleration of that elevator increases, the path of light traveling inside it starts bending more and more. Now imagine this. The elevator's acceleration becomes so extreme that the moment light leaves the light source, the elevator floor collides with that light at the same instant. Meaning, the light doesn't even get a chance to move forward. Pay attention. This is the same light that normally travels at a speed of 300,000 kilometers per second. If even something this fast cannot move forward, you can imagine how extremely curved space-time must be there. Near a black hole, almost the same situation occurs. Space-time bends so intensely that even the fastest moving thing in the universe, light, falls straight into the black hole. Now think about it in another way. Imagine that instead of Earth, there's a black hole, and instead of a cannon, there's a torch emitting a beam of light. The moment light leaves the torch, instead of moving forward, it starts bending downward and goes straight into the black hole. This happens because every possible path there leads toward the center of the black hole. Now you can estimate it yourself. When an object's escape velocity is so high that it doesn't even allow light to escape, how terrifying must that black hole's gravitational power be? That's why once anything crosses the event horizon, even light, it can never come back. Now, friends, this is exactly why we may never know what is inside a black hole. Because to see anything, light must come out of it. But a black hole absorbs even light itself. Now, friends, a black hole also has a boundary from where it does not allow anything to escape. This boundary is called the event horizon. As we know, the farther we move away from any celestial body, the weaker its gravity becomes with increasing distance. According to Einstein, the curvature of space-time also decreases as we move away from a massive object. In the same way, a black hole also has a limit up to which it can pull objects toward itself. Let's understand this with a torch experiment. As we know, nothing can move faster than the speed of light, which is the maximum speed limit of the universe. Now, if we slowly move this torch light away from the black hole, let's see what happens. When we shift the torch slightly upward, at this point the gravitational effect becomes weaker than before. So the light that was previously falling straight into the black hole now starts traveling along a curved path. If we move the torch a little higher, we will see that the light is able to travel even farther than before, but eventually it still falls back into the black hole. Now, friends, as we continue moving the light source farther away from the black hole, the gravity keeps getting weaker, and we observe that the light travels a greater distance. There exists a special point in space where if you place a light source and turn on the torch, the emitted light does not escape directly. Instead, it starts orbiting around the black hole. This boundary is called a black hole's event horizon. It is also known as the point of no return. The event horizon is an invisible boundary of a black hole. If any object, even light itself, crosses this boundary, it can never come back out. If we imagine the curvature of space-time, the event horizon looks like a whirlpool formed in water. Just as nothing can escape once it enters a whirlpool, in the same way, once something crosses the event horizon, everything moves only toward the black hole. Now, as we move the light source farther away from the black hole, its gravity gradually becomes weaker. The black hole still tries to pull the light, but as the distance increases, its grip slowly loosens. Because of this, light can easily escape outward. As distance increases, the black hole's escape velocity decreases, and light is able to cross it. This principle does not apply only to black holes, but to the entire universe. Gravity becomes weaker with distance. And because of this rule, planets stay in their orbits, the moon revolves around the Earth, and the Earth orbits the sun. This is the true nature of gravity. In our daily life, we don't even realize how every single moment gravity is running this entire universe. Friends, now comes the concept of gravitational time dilation. As we just learned, massive objects bend space-time. This means that heavy objects don't just curve space, they also affect time. Because as we know, space and time are actually one single thing. So massive objects change the flow of time as well. In the movie Interstellar, you saw that 1 hour spent on Miller's planet was equal to 7 years on Earth. Friends, this difference in time between two planets is not science fiction. It is a reality of the universe. In the universe, wherever gravity is stronger, the flow of time becomes slower. That means time passes more slowly there. And inside a black hole's singularity, time completely stops. Which means, if you reach a black hole's singularity, time will never move forward for you. By the way, friends, I've explained the movie Interstellar in complete detail, especially the ending, which most people find confusing. If you'd like, you can watch that video after this one. Now, friends, a question must have come to your mind. Why does time slow down because of gravity? And what exactly is gravitational time dilation? So, friends, gravitational time dilation is a broad topic, which we'll explain in a very simple and desi way in the next video, because this video has already become quite long. Till then, enjoy this Interstellar movie explainer video showing on your screen. I'll see you in the next video. Till then, goodbye.